Okay, first of all, welcome to this clinical art training, which is of March 2025 batch. And let me go into presentation mode and then, okay. So welcome everyone. So first of all, thank you very much for enrolling. So this is session 1 of the training. So what will we see in this training? So we'll see a quick introduction to R. We'll see a quick introduction to R tidyverse, and we'll see some basic differences between SAS and R. And we'll see a quick introduction to the tasks handled by a clinical trials programmer in general. So it's kind of a quick recap of the tasks typically handled by a clinical trials programmer. So about the trainer, my name is Anil, and I have a master's degree in pharmacy. And I am working in this field since 2013. And I contributed to the technical content on my CSG.in website, and I also contribute technical content on my CSG YouTube channel. And if you are interested, I work for a CRO as well. And some details about the training. So sessions will be conducted via Zoom meetings like the one which we are having right now. And meeting links will be shared on WhatsApp group and on the website training page. And users must be signed in with enrolled username to see the link. So this is not live yet, so it will be live in a day or two. So users can join the first 2 or 3 sessions to see if the training flow suits them. And if they think they're fine, they can continue from the second week. And starting second week of the training, so WhatsApp group will be updated to keep only the users who wish to continue further in the sessions. And material and further communications will be shared only with the users who continue in the batch. And enrollment on the website is mandatory for accessing the training material. And recording links will be shared from day 6 or week 2. And the users can download the recordings onto local system for future reference. And please remind me at the start of each session if I forget to record the session. And this is my first formal batch of art training. So it will be a learning experience for me as well. So we'll try to learn together. And as the group is large, so taking live Q&A may become impractical very soon. So we can send us a message if you have any specific queries. So we'll try to address as many as possible toward the end of the session if we have time. Otherwise, I'll take those questions offline and try to add relevant explanations or content will be added to the future session slides. And I know that some of you know me personally for privacy and administrative reasons, so please do not disclose my personal identity anywhere in the group or during the meetings. So how should you look at this training? So let me hide my floating meeting controls. Okay. So how should you look at this training? So in any programming language, there are multiple approaches to get to a result. Sorry, someone is annotating on the screen. I forget to disable annotations for others. Sorry for that. Let me clear all the annotations first and disable annotations. Okay, sorry for that. Okay. So in any programming language, there are multiple approaches to get to a result. Similarly, in R, there are multiple approaches to a single problem. Added complexity in R is there are multiple packages available, so the complexity exponentiates. So each package may have multiple solutions to a single problem. So that is kind of like if you are learning or seeing. Okay, so there are multiple packages available, so the complexity exponentiates. So there is nothing called right or wrong approach. So learn one approach first and then know about other approaches and then decide what works best for you. So you see this training as you are learning the very first approach or one approach of doing things in R if you're already familiar with R. So what will be covered in this training? So we will learn R programming equivalents to frequently used SAS programming features, and we will begin this with R tidyverse package. And once we become familiar with core programming features of R, we will implement R programming for unique concepts required in typical STTM programming. And we integrate the STTM programming concepts to create a few full domains. And same approach of unique concept programming and then integrating will be used for ADAM and TFLs as well. As part of the discussion related to unique concepts, we will cover the explanation of the underlying concept, and we'll also quickly describe the SAS code that is used for that concept. So what do we mean by unique concepts here? For example, if you work on STTM, there are concepts like your epoch creation, your visit mapping, you have your baseline flagging, you have your study day. So all of those unique concepts will be discussed extensively, and then we will try to integrate all the concepts learned to create a few full domains. So same approach will be used for our ADAM programming and also for TFL programming. So we'll discuss the concepts extensively first, and then we will jump to the programming, and then we'll see whatever concepts we have learned, we'll integrate all of them to create full domains. So what all things you will have access to as part of this training? So you will have access to the practice data and programs for all available lessons on the website. So how long will you have access? It will be 90 calendar days post your last session of the trainings. So you can take backup of the codes and data if you want to. So video recording links of the sessions will be shared in WhatsApp group, and the links remain active for 4 calendar days. So you can download the videos for your future reference, and post 4 days, the links will be inactivated and in general will not be able to help you much in downloading. So it's up to the users on to download as and when a link is shared right after the session. So what are some of the prerequisites for this course? So we assume that you are already familiar with base SAS programming, and you already have access to a SAS programming environment, and you should by now have installed R and RStudio as well. And once you install R and RStudio, as we are specifically seeing the course in terms of Tidyverse package, so you should install Tidyverse package and also load it in your sessions. So how can we do that? So we can install Tidyverse package with a simple single line of code in your R programming environment or RStudio scripts. So you have a function called install that packages. So you will have to specify the name of the Tidyverse to that install that packages function. So you'll be able to download Tidyverse packages, and to load the packages to be used in your SAS session, you have a function called library to load that function. So you can like these two lines of code should help us to start with installing the package and also make the Tidyverse functions available for us to continue with the programming. So let's start with what is R. So most of the definitions and descriptions will be short. I'll not go into the theoretical details because we are specifically trying to see some of the aspects in terms of Tidyverse package. We'll see the individual descriptions of those functions detail, but the introduction will be kind of quick and short. So what is R basically? So R is a programming language for statistical computing and graphics. So it is also a software environment. So what do we mean by a SAS and as a software environment? It has setup that allows us to create programs, run code interactively, and generate reports. So R is a programming language and also a software environment. So what is base R? Base R refers to the core functions and features that come pre-installed with R. So it includes fundamental functions for your data manipulations, statistical analysis, and visualization of the data. So while powerful and self-sufficient, base R can still be extended with packages to improve efficiency and readability. Okay, so base R has a lot of functions and features that should be sufficient enough to do data manipulation, statistical analysis, and visualization. But there are some packages which help improve efficiency and readability. So we'll be using some packages for that. So what is an R package? An R package is an extension of base R that provides additional functions to enhance R's capabilities. So think of it as an add-on that simplifies or extends what R can do. So packages are stored in repositories like CRAN, which stands for Comprehensive R Archive Network, and general repositories like your GitHub. So these can be installed into our R environment with simple commands. Like if you know about a package or repository that is available in CRAN, if you want to install it, you can install it with like how we have seen. We can install our tidyverse package with install that packages function of base R. So some examples of our packages. So we have a package called ggplot2. So it is used for generating some advanced graphs. And we have a package called dplyr, so dplyr. So it is used for data manipulation. And we have a package called survival package. It is used for analysis of survival data in clinical trials. So our packages help make coding easier, faster, and more efficient by providing ready-to-use functions for the specific domain of interest. So what is Tidyverse? Tidyverse is a collection of R packages designed for efficient, readable, and consistent data manipulation and visualization. So now we have a basic understanding of what is R, and we have come to the word about like what do we mean by R package, and we are specifically talking about the package that we are going to see. So what that is Tidyverse. So Tidyverse itself is a collection of R packages designed for efficient, readable, and consistent data manipulation and visualization. So it includes certain core packages like ggplot2, so which is used for generating visualizations or graphs, and we have a package called dplyr, so dplyr, so which is used for which has functions which help us in filtering the data, summarizing the data, and organizing the data. And we have a package called tidyr, which is used for reshaping the data. What do we mean by reshaping? So which is nothing but transposing our data. And it also has packages called readr or readexcel, which is used for reading data from external files like our text files, CSV files, or our Excel files as well. So it uses the overall tidyverse. It uses a consistent syntax with functions that are intuitive. So we'll see like what do we mean by intuitive like somewhere down the line in the course, and we'll see. And it has a concept of piping. So we'll also discuss that what do we mean by piping in a while. And then all of these functions are designed to work together seamlessly. So why are we learning tidyverse specifically? Clinical trial programming community is building or already has built packages to help with SDTM datasets, ADAM datasets creation, and our tables listings and figures creation as well. For example, we have a package called SDTM Oak that is meant for developing or helping with the tasks related to SDTM. And we have a package called Admiral, which helps us in, which has functions that helps us in creating ADAM datasets, and we have packages like tplayer or carver, which helps us in creating tables, listings, and figures. So all of the above packages are based on, or at least use the underlying concepts from Tidyverse. Okay, so we have like some things are already being built for STTM, ADAM, and tables, TFLs, but all of the underlying packages use the concepts from Tidyverse package. So learning R Tidyverse has to be seen as learning Scratch coding and all the above packages as macro repositories. So there were questions for me, like when I started saying like, why not start learning Admiral? So Admiral is an extensive package. It covers like most of the typically needed ADAM programming concepts covered. Just a second. But so there can be a time when none of those functions would be sufficient for our need. So in that case, so what we need to have our Scratch coding ready. So as these packages are based on Tidyverse, so if we learn Tidyverse, we should be able to Scratch code for the concept if there is no equivalent available in the standard packages. So what are the packages that are part of Tidyverse? So what do we typically do as a clinical trial programmer? So we'll try to associate with the task that we do, and then we will try to associate the packages that are available with the Tidyverse with those tasks first. So we do data manipulation. What do we mean by data manipulation? So we will be adding or dropping or modifying existing variables. So as part of our regular day-to-day activities, we also include or add our subset observations. We reorder the observations. We generate summary of the data. We have to merge our data sets and append the data sets as well. And we also restructure or reshape our data. So it could be transposing the data from wide format to long format or long format to wide format. And we may have to read data from external files like Excel files or text files. And we may have to work with text strings like detecting the presence of a substring or extracting a substring from a text variable. And we also work with datetime values, and we may also generate graphs as part of our day-to-day activities as a clinical trial programmer, or to be more precise, as a clinical SAS programmer. So we have some functions that covers for all the activities that we do as a clinical trials programmer on our day-to-day job. So we have a package, or we have a package that is called dplyr, which contains functions related to data manipulation. And we have a package called tidyr that helps us in restructuring or reshaping our data. And we have packages called readr or readexcel, which helps us in reading the data from external files. And we have a function called a package called stringr that helps us in manipulating the text strings. And we have a package called ggplot2, which helps us in generating the graphs. And we have a package called libridate, which helps us, or which has functions that helps us to work with datetime values. And we also have a package called haven that helps us in reading the data that is created in other statistical environments like our SAS or Stata, or it could be any other statistical environment. So commonly used statistical as a clinical SAS programmer. So we should be able to read the data from the SAS datasets that we have available, and we can make use of the functions from the package called haven to read the data. And we have a few more packages that we will see as on need basis. So what are some of the important functions that are available as part of the dplyr package? So we have a function called mutate, so which allows us to add or modify existing variables. And we have a function called select, which helps us in adding or keeping the required variables or dropping the selected variables. And we have a function called filter, which is used for subsetting the observations from a data set. And we have a function called arrange, so that helps us in reordering the observations. And we have functions left join, right join, inner join, and merge and full join, which helps us in joining the or merging different data sets. And we have a function called bind rows to append data sets. So we'll discuss about all of these functions in detail later on, but just to give you an understanding of what is available in these packages, I'm just listing them here. And we have a function called summarize to get the descriptive statistics for our numeric variables, and we can make use of the same function to get our counts and percentages as well. And then we said tidyr is one such package as which is part of our tidyverse. So we have two functions which are namely typically used for transposing the data. So in SAS, we use a single procedure called transpose to reshape the data from wide to long format and long to wide format. But in our tidyverse tidyr package, so it is two different functions. So if you want to pivot the data from long data to wide format, so we use pivot wider, and we have pivot longer to do the vice versa. And we have some functions which are coming from our readr or readexcel, so which is used to read the data from comma separated files or tab separated files. And we have a function, those are read CSV and read TSV. And if we have to read data from Excel files, so we have a function coming from read Excel package, so which is used to read, which is equivalent to our proc import of SAS. And then we have some functions which are in our stringr package, which is used for our manipulating the data in our character variables. So we have a function called str count, which is used to count the number of occurrences of a substring within a string. And we have a function called str underscore length to count the total number of characters available in a character variable or a text string. And we have a function called str detect to detect if there is a substring present in a full character variable or another string. And if we want to know the exact position of where the match is, we have a function called strlocate. And if we want to replace a string or a character string with another character string, we have a function called strreplace all, so which is part of our stringr package again. So we have a function called str to combine information from one or more different character variables. And we have a function called str sub to extract a substring from a string. So now we'll see some basic differences in R when compared to SAS. So first of all, R is case sensitive. So in R, var name, so with V and N there, and var name in all small case letters are different variables. In SAS, variable names are not case sensitive. For example, if you have var1 in all caps or all small letters or mixed case, they represent the same variable. So, but in R, they are different. So dataset names are case sensitive too. So for example, the class with C capital and class with C in small case letter, they represent two different data. So they do not represent the same thing like in SAS. And the second thing is equals to sign. So in SAS, we do not have the concept of double equals to sign. So we only have single is equals to sign. But in R, we have double is equals to, single is equals to, and we have something called as an assignment operator. So here that is, but it is a two character notation. So we have less than symbol followed by a hyphen. So we call that as an assignment operator. So in R, so we use double is equal to sign in comparison. So if you want to check if the variable named x has a value of y, you will have to use double is equals to sign. And if you want to assign a value of y to a variable named x, so you will have to use this assignment operator, which has this sign of less than sign followed by a hyphen. And then we also have is equals to in R, but in is equals to is most probably used in assigning something as part of a parameter value to your parameter and the function. So for example, here I am making use of is equals to sign to specify that x is equal to parameter of the main function has to use a value of my data. So is equals to is used for assignments, but most of the times it is only in passing arguments to your functions, passing arguments to your functions. And in SAS, so we know that is equals to sign is used for both assignment and comparison, but these are the things that you need to keep in mind. So there are different. So for comparisons, you will have to use double is equals to. For assignments, you will have to use assignment operator. And for assigning values to the parameters within your macros function, your functions, you will have to use your is equals to sign. But again, this will come more natural to us once we start programming. But just for the sake of awareness, so I have listed them here. And then we have some concept called piping within our tidyverse. So it uses pipes to chain operations smoothly. So for we have a symbol called this percent greater than percent sign. So we call this as pipe. So which is used for chaining operations smoothly. So what do we mean by chaining? So for example, here here is a full or basic R code making use of tidyverse. So what does this do is, so we are starting with a data set named df and we are passing it into a function called filter to filter the observations where age is greater than 30, and we are passing that resulting filtered rows to a function named select to filter the variable to keep only the name and age variables. So this is what we call as piping. So we are chaining one operation to the next operation. So we are starting with data set name df and we are passing it into filter function and the resulting rows are passed into select function. So we are chaining something literally. So we use this symbol called pipe for chaining. Okay, so that we do not have an equivalent of it in piping. So if you have to run a proc sort and then use that sorted data set in the next data step, you'll have to create those intermediate data sets and write those steps separately. But here we can chain them together. Okay. And the next different key difference when compared to SAS in R is your how missing values are handled or represented. In R, missing values are represented as NA, and we have certain functions like isNA to help manage them. We'll see this in later on, but just know that the missing values are represented with NA. And whereas in SAS, the missing values are represented with dot for numeric variables and blank or null codes for our character variables. So in R, so blank space is not same as NA in R. So if you are as a SAS programmer, we tend to check for if variables value is not is equal to missing to check for non-missing values, but that will not work in R. So we'll have to make use of functions, explicit functions that are available to check for missing values in R. So length of character variables is another one thing that will that has a key difference. So in R, character strings do not have a fixed length and they do expand as needed. Okay, in SAS, whereas we have a fixed length for our character variables, and if we say a length of 20, it means it stores a maximum of 20 characters by in general. So, but in R, so we do not have a explicit concept of length for a character variable. And if we are increasing or assigning a text bigger than the previously assigned values, it automatically expands and takes the value automatically. And then we have data structures. So R supports various data structures like vectors, lists, data frames, matrices, and factors. But the closest equivalent for a SAS dataset in R is a data frame. Okay, but there is no direct equivalent concept, at least as a clinical trials programmer, we might not have seen any data structure which are related to our vectors, lists, matrices, or factors directly. Okay, but there are other data structures available, but we will touch them on need basis, but will not go extensively into that. So the equivalent structure for a SAS dataset in R is a data frame. And again, so R has this native structure, which is called data frame, and it has some default behaviors that make working with them a little difficult in data science. So we'll try to cover this, what are those default behaviors later on. But so for time being, you just remember that we will not be directly working on our native data frame structure, but we'll be using a data frame structure that is part of our tidyverse package, and that is called a tibble. So they define tibble as an improved data frame that makes working with data easy. The underlying reason is, so the data frame structure of native R or base R has some default behaviors. So that makes some assumptions and some automatic conversions happen in that data frame, but that is typically not expected to be happening when we are working with clinical data. So we and Tibble overcomes or removes all those default behaviors which make working with data a little tough. So we will be using our Tibble based data frame so that our data work as clinical trial programmer become easy. So continuing with the basic differences in R when compared to SAS, so we have data type differences as well, data types of variables within a data set. So we know that SAS only has two data types, one is character and numeric. R has more data types, which includes character, integer, double, logical, factors, etc. So we have a data type called integer, which is used to store whole numbers, and we have a data type called double, which is used to store floating point numbers, which we have done for the numbers where we have decimal places available, and we have something called as factors. So it is a for character variables. So if even if it has a fixed number of levels, we use the same notation of character variable in our SAS. But if there are fixed levels available in a particular variable, so SAS R stores them as in a data type called factors. So it creates levels and associates some indexes for that. We'll see in detail later on what do we mean by factor. But for now, remember that if a character data in a variable is expected to have finite set of values, so we can convert them into a data type of factor. Okay. And then we have a data type of logical, which is used to store the values of true or false, and we do not have a direct equivalent of it in uh, SAS. And then we have date and date time data types in R, but in SAS we know that date and date time values are stored as numeric values in terms of number of days from 1st Jan 1960 and number of seconds from 1st 12 a.m. of each day for time values. So, and we have a concept of open variables or objects in memory in R, but we do not have a equivalent of it in SAS. Okay, so there is variables can only be part of or created within a data set within a data step in SAS, but we can create variables and other objects also in memory in R. So we'll see like these things as on need basis, and I'll touch upon this concept whether we are creating a variable in memory or whether we are storing a variable as part of a data set. Okay, but just for awareness, know that there are concepts like objects in memory where there is no equivalent of it in SAS, or at least as a clinical trial programmers, we would not have used any of those concepts because SAS is also extensive and the amount of SAS that we use as a clinical SAS programmer is very limited. Okay, so we have 27 more minutes. So I'll now jump to some of the a quick introduction or recap to the clinical domain. So what do we do as a clinical trial programmer? So a quick background. So we know that clinical trials are conducted primarily with the objective to check efficacy or safety of a particular treatment. And we start with a preparing with a document called study protocol, and protocol lists all the data that must be collected, and forms will be created to collect the data. So we end up having clinical trial data collected. And what do we do as a clinical trial programmer? So we programmatically organize the collected data into standard structure in tabular format. And then we create additional data sets to handle any derivations needed for analysis of data. And then we create our summary tables, listings, and figures. And then finally, the interpretation of the results happen. So what do we do? So we have data collected and we are programmatically transforming that into a standard structure. So typically, if you are following CDX standards, so that will be our SDTM datasets. And what do we do next? So we may have to derive some things. So on the collected data to handle or to perform the analysis of data. We typically call these as analysis datasets, but if we are employing CD standard, so we call the analysis datasets as ADAM datasets. And then we use the ADAM datasets to create our summary tables, listings, and figures. So what type of data is typically collected in a clinical trial? So we will have the demographic information collected like age, sex, race, and ethnicity of the participants. And we'll also have the medical conditions related data experienced by the subjects in the recent past or which are ongoing. And we also collect information related to the prior or ongoing medication. And we collect information on the usage of substances like caffeine, tobacco, alcohol, etc., as these may impact how drugs act in the body. And then we also track the usage of study medication while the subject is on study. And we collect information about any adverse events experienced by the subject while on study. And then we monitor vital signs like blood pressure, pulse over the course of the study. And then we also monitor the changes in ECG while on study to evaluate whether the drug or the treatment is impacting the safety of the participant. And we also try to perform some laboratory tests on blood, urine, etc. to assess the impact of the drug on the patient. So how do we organize data in electronic format? Let's say there is a clinical trial being conducted in which two participants are enrolled. So let's say a male patient who is identified with number 1001 is of 52 years age and belongs to Asian race. So this is kind of a textual description of a participant. And a textual description of the second patient is, so patient identified with number 1002 is a 49-year-old male and belongs to white race. So what do we do with this? So we will not be able to make any analysis because if the data is collected in textual format, or so if we have to perform some analysis, it will be helpful if we have the data that can be read or interpreted with machines, right? So for that purpose, we organize the data in tabular format with rows and columns. So typically a row corresponds to an entity. So here in this case, as we are collecting the information related to the participant, so a patient in this example is considered as an entity. And a column corresponds to an attribute of the participant or that entity. And a row is also called as an observation, and column is considered as a variable. So whatever data that we collect as part of the clinical trial, so we organize that data into a tabular format with rows representing observations and column representing attributes or variables. Okay, so this is how the data that is collected in a clinical trial will be coming to us in the form of tabular format. Okay. So another example of organizing data in electronic format. So this is talking about in terms of adverse event. So while on study, the patient 1001 experienced a moderate headache from 5th Jan 2010 to 8th Jan 2010, and the study physician judged that the headache is not caused by the study treatment. So this is the textual description of a adverse effect or side effect seen by the participant in a clinical trial. So we'll not be able to perform any analysis or see trends or patterns if we have the data collected in textual format. So for that purpose, what do we do? So we convert that into a tabular format with rows representing entities or columns representing variables or attributes. So here in this case, the entire textual description provided here is converted into a tabular format in terms of subject ID, event experience, the start date, end date, and the severity of that event, and the causality or the relationship to your study treatment being stored in its own column or variable. So we'll see another example on how we organize the collected data into tabular format. So let's say a clinical trial that is identified with the abbreviation of MyCSG, and systolic and diastolic blood pressure of patient 1001 were 130 and 80 respectively when measured for month 1 visit on 5th Jan 2010. Again, so blood pressure was 120 by 80 for a subject 2003 on 9th Feb at month 1 visit. So if we see this again, this is textual description for two different tests. So one is systolic blood pressure and the second one is diastolic blood pressure. So we can organize that into a tabular format with columns meant for. So we have said that the study is related or associated with an abbreviation called MyCSG. We have a variable for it in order to store the patient related information. So we are using a variable named uSubjID, and we have two different tests that are performed to indicate which test is that. So we are using a variable or column labeled as VS test CD. So we have representing the information of systolic blood pressure and diastolic blood pressure results in a variable named original result VSORRES, and the sample or the test date when that test is being performed is being stored in a variable or column named VSTTC, and the label or visit label associated with that is stored in a variable named visit1. So we are so whatever data that is being collected, so we will have to organize that in a tabular format so that we can use that data in our machines or electronic systems so to perform some analysis. Okay, so these are some typical structures that can be seen or how you get your data. So you get your data in terms of tabular format with rows corresponding to entities and columns corresponding to your attributes or variables. So what is the importance of having a standard? So what do we mean by organizing data in standard format? So, okay, I think I missed some link. So we said that, so we collect data in clinical trials and we store that in tabular format. And at the initial slide, I said like we will be converting the tabular data into standard structure using programming. So what do we mean by organizing the collected data into standard format? So let's say there is this simple form which is used to collect the demographic details of the participant. So which has 4 different questions: the subject number, gender, age, and race. Let's say the same form is being used by different clinical trial data producers, and they may end up creating a data set like this with the variable subject, gender, collected underscore age, and race, and they may name the data set as demo. And let's say another same form is being used by another data producer, but they may use different naming conventions. So here in this case, they are using a different dataset name. So with the variable names, though the same, but if you also note, and the collected age, the unit or the age is also being part of the variable itself. And so let's say it is given to someone else and they are reporting the same information in a different data set named with different naming convention for the variables and values. So let's say this is given to another data producer and they are giving us the data from coming out of this form in this structure. So the same data could be represented in different naming conventions and different variable naming conventions and value naming conventions as well. So if we do not have any data with a simple form which is only having 4 different fields, so we end up with different naming conventions for data sets, different naming conventions for the variables and for the values as well. So it will be of an advantage if we have a standard format for the standard data that is typically expected to be collected in the clinical trials. So that's where the standardization comes into picture. So let's say someone told us that demographics information, if it is collected in the study, must always be present in a domain or file named DM. A separate observation must be created for each participant. The subject number must always be in a variable named subs-ID, and sex of the participant must always be in a variable named sex, and the collected age must always be present in a variable named age, and associated unit must be in age-u variable. Race of the participant must always be represented in a variable named race, and the value of sex variables can only be any of f, m, or u. So the value of age-u variable can only be years, months, weeks, days, and hours. So let's say someone is telling us that, so if you are collecting demographics information, so these are the rules that you will have to follow. So anyone who generates this data set, who uses this form to collect the data, they will end up creating the data set which looks like this. So what is the advantage of having the standard? So finally, like we said, like the clinical trials data will be collected and we submit it to the regulatory authorities to get an approval for our medical product. So at the end, the reviewers will be able to see the data in a uniform format. So that's where the whole standardization comes into picture. So what does it mean by when someone has told us to organize data in a particular format? It means, so there is a standard that tells us how to organize the collected data and that there are also advantages if we organize data in this way. So what is the standard for organizing collected data? So the standard name is Study Data Tabulation Model. So who created this standard? So there is an organization called CDISC, so which is CDISC stands for Clinical Data Interchange Standards Consortium, and this organization has developed and is maintaining clinical standard called SDTM, which is used for standardizing the standard organizing the data in a standard manner for your collected data. So let's try to understand the different words that are part of your clinical data interchange standard consortium. So we know that CDISC stands for Clinical Data Interchange Standards Consortium. Why do we have clinical data in place? Because we are dealing with the data coming from clinical trials. So we have clinical data in that. And then we have this word called consortium. So the word meaning of consortium is nothing but an association, which is typically of several companies. So this CDISC is a group which consists of members from data producers and data users and also the programmers. So who are the primary data producers? We have the pharmaceutical, biotechnological companies or the device manufacturers who are involved in conduct of the clinical trials. And who are the primary data consumers or data users at the end? The primary consumers for any clinical trial data would be the regulatory agencies with respect to a specific country. So we also have programmers or technology development companies are part of this consortium. So as the standards are built on a consensus basis, so we have people from pharmaceutical or biotechnological companies who are who are the data producers, and we have members from regulatory agencies who are the data users at the end. And we also have, as programmers, work with data in manipulating from the collected data to standard structure and in terms of creating analysis data set and final creation of our tables, listings, and figures. So people from these three backgrounds, data producers, data users, and programmers, are part of this group. So hence the word consortium is there. And then next is our interchange standards. So the basic word meaning of interchange is to exchange data between two parties. So as this CDISC is meant for creating the standard which supports the interchange or exchange of data between data producers and data users, the word interchange standards is there for us. So CD is for clinical data, IS is for interchange standards, and C is for consortium. So then what do we mean by creating additional data sets? So as part of the role of like what does a clinical trial programmer do? So we said we organize the collected data into standard structure and we call that as SDTM, and we quickly saw like what do we mean by SDTM. And then we also said that we use additional data, we create additional data sets. So what do we mean by creating additional data sets? So let's say there is a clinical trial in which the endpoint of interest is the change from baseline in mean arterial pressure at month 1. So there are some technical terms in this statement, but for time being, let's assume that we are all aware of like what do we mean by blood pressure. Okay. So mean arterial pressure is a derived parameter for which systolic blood pressure and diastolic blood pressures are needed. So sys-BP and dia-BP are collected at least once during screening period and at month 1, because for the trial to see the impact, so we are interested in seeing how the mean arterial pressure is varied at month 1 when compared to the baseline. So as we wanted to see the change, so we should have collected the data for systolic and diastolic blood pressure at least once during the screening period and also at the specific time point of interest. Here in this case, it is month 1. Okay, so but mean arterial pressure is a derived parameter for which we need to have systolic and diastolic blood pressure collected. So for collection, so we'll make it in terms of systolic and diastolic blood pressure at 2 different time points. Again, for analysis purposes, so we have seen that, so at least once the collection would be made during screening period. And if there is more than one collection, so we are being asked to use the latest record for baseline. Okay. So we are collecting data once or more than once during screening period. If there is more than one collection, so we are being asked to use the latest value for our comparison at month 1. So for this analysis, so what is that we need? We need some derivations. Okay, which means like if we have more than one collection, so we need to identify which of those have to be used for comparison. So we have to identify those records. So if we are following Adams standard, we create a variable called ABLFL to store or indicate which record is being used as your baseline record. And before that concept of baseline, so let me see. So we only will be able to collect systolic and diastolic blood pressure on our case report forms. But mean arterial pressure is a derived parameter. So we will have our systolic blood pressure collected, diastolic blood pressure collected. But for analysis, we need this derived parameter, which means we will have to use the values of systolic and diastolic blood pressure and derive something. So which is not part of the collected data. So we were saying that in SDTM data is nothing but a standard representation of your collected data, but we need an additional parameter or additional test that is to be created from the collected results. So we have additional derivation, and we also needed to identify which record is being used for comparison if there exists more than one record during the specified period of screening. So which means again a derivation is involved. And then the analysis interest is change from baseline, which means you want to compare your result with your baseline value and then derive that change. Okay, so which means in your collected data, you only have your systolic blood pressure and diastolic blood pressure and the times when those were collected. Out of all those collections, some will become your baseline and you will have to derive your parameter and you will also have to derive your change. So which means, so some additional derivations are needed to so that you perform your final analysis on the change from baseline. So all those derivations are not part of your SDTM because it is just a representation of your standard collected data. So all those derivations will be handled as part of creating our additional data set. So these additional data sets are generally called as analysis data sets. So is there any standard from CDISC for analysis data sets? Yes, and we call it as analysis data model. So what does ADAM standard specify? It defines the standards for analysis datasets for efficient generation, replication, and review of clinical trial statistical analysis. So how do we use these analysis datasets? So we use these analysis datasets to create reports in the form of tables, listings, and figures. So let's now see like quick introduction to the TFS. So here is a summary table, so which is summarizing the data for demographic characteristics of sex, race, age, weight, height, and BMI. So let's assume that this report is based on a clinical trial in which 3 different dose levels of a medication is being compared. So we are trying to summarize the data in terms of how many number of subjects are there part of that treatment and how many of those participants within that particular treatment group are male or female. And we are segregating or seeing a summary of how many number of subjects are part of each of the racial groups. And we are seeing the mean age, average age, and minimum age and maximum age of each of the subjects in that specific treatment group. So why do we create tables? So we try to see if there are any trends or patterns that could be attributable to a particular treatment. Okay, attributable to a particular treatment. So we have the data collected, we will have our analysis data sets created, and we generate our TFL. So here on the screen is a example table that we create as a clinical trial programmer. So we again typically try to make some assessments or inferences using the data from the tables. So here is another summary table example wherein we are summarizing the vital signs data. So in terms of the result and the change from baseline value. So here we are seeing the data for systolic blood pressure. So over different treatments over different time points. So we have active medication being compared with placebo over different time points, and we are seeing what is the individual values for systolic blood pressure, the actual results, and what is the change from baseline in terms of the n number of subjects with available data. Now, what is the average change from baseline and what is the standard deviation at over different time points is being summarized. Again, we use data from the tables to use or to make an inference about whether a particular treatment is behaving in a particular trend when compared to the second treatment. At one point, we would be interested in seeing the data at subject level, right? So in tables, we are just creating or comparing the results across different time points, here in this case, across different treatments. But here we will not be able to know what is happening to a specific subject, but we are trying to summarize the data for all the subjects who are being treated with a particular treatment. But at one point, we would be interested in seeing the data in terms of what is happening to a specific subject. For that specific purpose, we generate something called as listings in clinical trial programming. So here is an example of a ECG results data. So here wherein the data for the subjects is listed over different time points. And all of the, again, so we'll go into the details when we extensively cover, but the basic difference between a table and a listing is you will present the data at subject level in your listing, whereas in treatment in a table, so the comparison will be made across all the subjects within the treatment that you have within your study. And then we generate figures. So figures again can be representing like a summary data or data at subject level. So this is an example figure that we may generate in our study. So which is nothing but a graphical representation of subject level data or summary level data can be generated. So this is a typical, again, so some of you might already be working and you are familiar with all of these things, but as a group as a whole, like we have some mixed group who have not worked extensively on all of these things. So I try to make this opportunity to quickly recap or introduce what we do as a clinical trial programmer. So we end up with your collected data, you convert that into your STTM data sets. You use the STTM data sets to create your analysis data sets, and you use the analysis data sets to create your tables, listings, and figures. So now we'll see, like later on in the session, we'll see how we will be able to get to use R to generate your STTMs, your ADAMs, and TFLs. I'll stop here. We only have 5 more minutes left. Uh, I'll take a few questions if you may have any.
Yeah, thanks, Anil. And I have a quick question. Do we have any first start, last start concept available
Yes.
in R?
Yeah, we'll see. Like there is no direct equivalent of it, but we'll be able to get to that same result.
Okay, thank you.
Yeah, we'll cover that starting tomorrow. So we'll see all the equivalent that we have available, like whatever we do as a clinical SAS programmer. So I'll try to cover all the equivalents in SAS in R first, and then we'll see how we can make use of those concepts in our STTM, ADAM, and TFL programming. But the same result of counter variable creation, first record subset and last record subset can be done.
Okay, thank you.
Anil, we have macros in or like equivalent for macros.
They call it as functions. It's the same thing, but the final intention is like you pass some parameters and then get some end result of it. We call it as functions in R.
And one more thing, do you teach SDDM work and also Admiral?
No.
Because in companies, I feel like they use packages, so it's better to have some
as part
knowledge
of
on
the
this.
course, I'll not be touching base on any of those things, because that itself become a standalone training, and I myself have not extensively used SDM Oak, but I have some exposure to Admiral, but I have not used Oak yet.
Okay.
Because the main intention is to cover you the basics of like calling it as scratch coding. Even if something fails and if there is no equivalent of it in your package, you should still be able to write coding. So without learning all of these basically you will not be able to cover like readily use your existing packages also, right? So once you learn these things, like you will know like, okay, for this equivalent you already have a function in that package and you'll start using it. But at one day, like that exact equivalent may not be working for you, or you have an added dimension to the existing function. So you should be able to fall back and use your scratch coding. So the main purpose of this training is to help you build with that scratch coding thing.
Okay, yeah.
Can you provide this document as a reference?
Sorry?
Can you provide this document or PPT for
PowerPoint slides will not be shared, but because I am already sharing the video recordings, slides as such will not be shared.
Okay.
So any material that will be available will be part of the SAS, and our page of the website in a different format. That's all. In short, all the content that I'm presenting here is being picked from, like, will be picked from the material available on the website, which you will have access to.
Can we get the download video or maybe the temple links how to download and all?
It's a simple thing like how you install any software, but maybe I have not made any exclusive video, assuming that you should all be able to do that. There are already resources available. Maybe you can just simply search for like install R and R Studio in the internet. You will get some videos and also text description of that. How you can do that is already.
Yeah, can you share that in the group?
I'll do that then. I'll do that. So there seems to be a couple of messages. Can we get our download links demo video to download? Which SDTM? Okay, so again, so there is a question on which SDTM ADAM domains will be created. So my approach is not specifically related to any domain. So how I see is like we are on top of time. So my approach is like, as I was mentioning in the description, so we will be covering the unique concepts required for like, there are some 10 to 15 unique concepts that will be required to program any SDTM datasets. Which means when I mean like 10 to 15 unique concepts that are typically needed. So we'll cover all of those concepts extensively, and then we'll see how we can make use of all the concepts to integrate into create a full domain. So again, so we will see a few domains, but this approach is not specific to a specific domain or therapeutic area. Main intention is to equip you with the general concepts required for getting to program a SDTM dataset, because if you see majority of your SDTM datasets will be findings domains, and the concepts required for a findings domains are limited, like 7 or 8 concepts. So if you master all of those things, then you will be able to create any findings domain. So the approach is not specific to your domain, but the underlying concepts required for the domains or datasets that are used. So same thing is for your ADAM. So you have certain concepts of parameters creation or derived records creation in your ADAM. So we'll see those extensively, and then we will work to integrate all of those things to create a few full Adam data sets. And then same concept of like for your TFL programming as well.
And what you will be sharing in tomorrow's class?
We will start with SAS, our equivalents of SAS programming features. For
Okay,
example,
thank
so how we add variables, how we sort the observation, those kind of things. So next 2 to 3 sessions will be on that. So our programming equivalents of SAS, and then after once we are familiar with all of those things, early next week we'll jump into how we can make use of our programming to program for our STTM concepts.
Hello, sir.
Yes, please.
In your website, R is telling it's under maintenance. So
It will
when
be
it will
live
be-
by today evening or tomorrow.
Oh, okay.
So we made some updates and it was breaking, so we had to put that maintenance. Maybe it should be available by tomorrow latest. Okay, I'll stop here. We'll meet again tomorrow. Thank you all. Bye.
you. Thanks. Bye.